Now in this video, what I'm going to do is I'm going to complete rotational motion. So this video, 2 or 3 questions are from core concept of rotational motion. Okay. The remaining part of the problems are from gyroscopic acceleration. See, even though gyroscopic acceleration are not inside your core syllabus, then also question have been asked. Okay, the fundamentals of gyroscopic acceleration are there. Okay, and I have explained gyroscopic acceleration if you go on to see the earlier parts of this chapter. Okay, not earlier parts of this chapter during the circular motion topics. Okay, so let's not waste further any more time. Let's focus on the question. Okay, so in this question, a small disk and a thin uniform rod of length L. Okay, okay, there's a small disk and a thin uniform rod of length L. Well and fine. Okay, whose mass is n times greater than the mass of the disk. That means what if the mass of the disk is m? The mass of the rod is n into m. Lies on a smooth horizontal plane. Horizontal plane means the gravity force is inside the plane. That means there is no component of gravity out here. Okay, the gravity means there is no portion of gravity acting out here. All the gravity forces are inside the plane of paper. Okay, the disk is set in motion. That means this disk out here. Okay, it is given a velocity v. And fine. The disk is set in horizontal motion and perpendicular to the rod. Okay, my diagram is fair. With velocity v, after which it elastically collides with the end of the rod. That means this disk out here. Okay, this disk is colliding at the end of the rod. Understood? Okay. And find the velocity of the disk and the angular momentum, angular velocity of the rod after the collision. So what is happening is, suppose this is a rod, some ball is colliding out here, and after collision, what will happen? This rod will move up and try to rotate. Understood? So this kind of motion is happening. This is colliding, and this is rotating and moving up. You have seen those conditions during pen fights. When you fight with your pen, you do something like this, you tickle it like this, and it moves forward and rotates. No, so same kind of situation is happening out here. So this rod out here, okay, of same length, same mass, it will try to go up with velocity of center of mass, and also try to rotate with angular velocity omega. Okay, and the type of collision is elastic. That means if this ball, okay, collides with velocity v, that means it will rebound with some other velocity v dash. So some other velocity of rebound is given v dash. And since I do not want to confuse, the direction of plus and minus, let's give the velocity v dash in same direction. Okay, and this previous situation, this is before collision, and this situation is after collision. Okay, so we have to find out the final velocity of center of mass, after which the elastic collision of and the velocity of disk and the angular velocity of the rod. So to find out the value of omega and v dash. Fair and fine. My first question is, what are the equations that I can apply? Can I apply conservation of linear momentum? Of course, I can apply conservation of linear momentum. So let me apply conservation of linear momentum. Okay. So conservation of linear momentum. Conservation of linear momentum. What does conservation of linear momentum say? m1 v1 plus m2 into 0 is equals to mv dash plus this mass into velocity of center of mass. So mv plus 0 is equals to initial total momentum is equals to final total momentum. mv dash plus n into m, mass of the rod, into velocity of center of mass. So this is my first equation. And let me make my first equation neat and clean. I'm cancelling out the m. Okay, I took the m common and cancelled out the m. Okay, so my final equation of conservation of momentum got somewhat like this. So this is my equation number 1. Okay, and what more equation can I apply? If the collision is elastic, can I apply coefficient of restitution? So coefficient of restitution. What coefficient of restitution says is that velocity of separation is equal to velocity of approach. If coefficient of restitution is 1 for elastic collision, velocity of approach. Suppose I take my frame of reference out here. What is velocity of approach? mv, isn't it? So mv. Okay. Now if I change my frame out here, what is velocity of separation of this point? Okay. So whenever collision is occurring, okay, you have to take the velocity separation and velocity of approach at the point where the collision is occurring. So this is the point where the collision is occurring. So what is the velocity of this point? The velocity of this point, this end point, is nothing but velocity of center of mass in forward direction plus omega into L by 2 in this direction, isn't it? So velocity of center of mass plus omega L by 2 is the velocity of this portion of the block. Understood this much? So this is nothing but velocity of center of mass plus how much? Omega into L by 2. So coefficient of restitution is nothing but velocity of approach is equals to velocity of separation. Now if I take my first frame of reference out here, I have to take my frame of reference now of velocity of separation out here. Okay, so if I take my frame of reference out here, it is nothing but minus VCM Acha. So what is if I take my frame of reference, is nothing but VCM plus omega L by 2 minus V dash. Okay. So this is my coefficient of restitution. Understood? Okay. So if I want to apply my conservation of angular momentum, my favorite axis is this one. Okay. So let me check. The initial angular momentum, if this is the origin, see, r sine theta is nothing but 0 because v vector and r vector are lying on the same line. Okay. So sine 180 is equals to 0. So initial angular momentum due to this particle is 0 and this particle is not rotating only. So 0 is equals to, what is the final angular momentum of the rod about this point? It is nothing but angular momentum of the rod about center plus velocity of center of mass through this point. That means it is nothing but ml square by 12, or sorry, nml square by 12 into omega. This is clockwise torque. That means velocity of center of anti-clockwise torque. Okay, this omega is trying to rotate in anti-clockwise. And if I take my origin out here, velocity of center of mass is trying to rotate in clockwise direction. So minus m into r cross v. So nm into what is r? L by 2 cross v, velocity of center of mass. So I get my three equations. From these three equations, what do I have to find out? I have to find out the value of omega and velocity of center of mass. So if I have to find out the velocity of omega and velocity of omega and v dash. Okay. So the most redundant variable out here is nothing but velocity of center of mass. So see, using these two, velocity of center of mass omega is not out here, omega is out here. Okay, v and v dash. So using these two equations, let me omit the value of velocity of center of mass because I do not need this variable for velocity of center of mass. So using these two equations, v minus v dash by n is equals to velocity of center of mass, and out here I'll get velocity of center of mass is equals to v plus v dash, okay, minus omega L by 2. Understood this one, these two. Now if I combine these two equations, suppose I'm combining these two equations, okay, I'm combining velocity of center of mass out here and velocity of center of mass out here. What do I get? V minus v dash by n is equals to v plus v dash minus omega L by 2. Okay. So still there is a pertinent value of omega. Okay, let me check. Okay. So if I solve these two equations, well, let me solve these two equations for omega. VCM is nothing but this one. Out here, VCM will be nothing but. Let me cancel out the n into m. Let me take it common. Okay. 2 and this becomes 6. Okay. L and L square gets cancelled. Okay. So I'm left with nothing but omega L by 6 minus velocity of center of mass. So omega L by 6 minus velocity of center of mass is equals to 0. So omega L by 6 minus velocity of center of mass is equals to 0. So I already got it. I do not need to solve this. This is very stupid equation. Okay. So I already got velocity of center of mass is equals to omega L by 6. Okay. So I already got my thing. Or out here, v minus v dash by n is equals to omega L by 6. Okay. And out here, I'll get omega L by 6 is equals to v plus v dash minus omega L by 2. Now somehow if I take this, but let me just separate it, this one. Let me just take this omega L by 2 to the right hand side. Okay. If I take to the right hand side, it will become plus. So 1 by 6 plus 1 by 2 is how much? There's nothing but 6. 1 plus 2 3 is 3. There's nothing but 4 by 6. 4 by 6 is nothing but 2 by 3. So I'll get 2 by 3 omega L. 2 by 3 omega L is equals to v plus v dash. So let me substitute this as 2 by 3 omega L. Okay. So 2 by 3 omega L is equals to v plus v dash. And let's do this one. Let me cancel out this one. Okay, then fine. Now what do I need to do? Okay. Now I got the relation between. First I need to find out the value of omega. So when I need to find out the value of omega, I'll just omega L is equals to 6 v minus v dash divided by n. Out here, omega L is equals to 3 by 2 v plus v dash. Now if I equate this with omega L and omega L, these two omega L, okay, I'll get 6 into v minus v dash by n is equals to 3 by 2 v plus v dash. Okay, so 3 2, these two would go out here and become 4. Let me make it neat and clean. Okay, so I get my equations as that 4v by n minus 4v dash by n is equals to v plus v dash. What do I need to find out? V dash. So let me take this v dash to the right hand side. So 4v by n minus v is equals to 4v dash by n plus v dash. Okay, or 4n minus 1 into v is equals to 4n plus 1 into v dash. Okay, or v dash is equals to this value. So I already got the value of v dash. Now suppose I want to find out the value of omega. So out here I do need to separate the value of v dash. So how do I do that? Same equation. Instead of solving for omega, isolate the v dash and find out the value of omega. Okay, v dash is equals to some equation. Out here also v dash is equals to some equation. Equate both the equation, you'll get the value of omega. Okay, and if you do that, you'll get somewhat omega is equals to 12v divided by how much? 4 plus n into L. Okay, and now the second part of the question is asking for what value of n. Okay, the value of velocity of center of mass VCM is equals to 0. So velocity of center of mass is nothing but omega L by 6. So if omega is equals to 0, velocity of center of mass can be equals to 0, no? So if I want to make this 0, okay, and velocity of center of mass is equals to omega L by 6. Okay, okay. So it doesn't matter what you do, the velocity of omega 1 be equals to 0. So there would be some velocity of center of mass. So let me see the question again, what the question is actually asking. Okay, I may have jumped the gun out here. At what values of n will the velocity of the disk after the collision be equals to 0? Achha, the v dash should be equals to 0, not this omega is equals to 0. After I have to make v dash is equals to 0. So if v dash is equals to 0, you can clearly see if I take n is equals to 4. If n is equals to 4, I can easily say v dash is equals to 0. Okay, so this is our question. Understood? Now to understand this question, the first thing that you must learn is just watch this video. Okay? If you watch this video, then I can explain from there. So let's watch this video. Okay?
And essentially, me and this bicycle wheel are one isolated system.
Observe carefully.
Platforms are isolated. And as long as there's no outside forces, or technically torques, but when we go into that, acting, then me and this bicycle wheel, our angular momentum should be conserved. Okay.
He's spinning the wheel.
Okay, so if it does have a lot of angular momentum already, and I try to change it by flipping it over, what do you guys think is going to happen?
After spinning the wheel, step on the platform.
Okay, I guess I told you already.
Okay, see? And while the wheel is spinning, see?
No?
One thing you must observe out here is while the wheel is spinning, he spun this thing in this direction, and as a result, this also started spinning. Okay, so these three things you must observe. Okay, now let's observe the same thing with vector quantities. Okay, the same video. Okay, so in this video,
And essentially, me and this bicycle wheel are one isolated system. Right? The platforms are isolated. And as long as there's no outside forces, or technically torques, but when we go into that, acting, then me and this bicycle wheel, our angular momentum should be conserved. Okay.
Okay, let's see the direction of spin. Is spinning in this direction. Okay, let's say this to be omega naught. Okay, so the omega vector, if you use your right hand, omega naught vector is in this direction. Understood this much? Now let's watch further part of the video. Okay. On further part of the video, he's spinning in this direction.
Okay, so if it does have a lot of angular momentum already, and I try to change it by flipping it over, what do you guys think is going to happen?
Now he's stepping on the platform.
I guess I told you already.
Now see. Okay, let me rewind a bit.
Okay, so if it does have a lot of angular momentum already, and I try to change it by flipping it over, what do you guys think is going to happen?
He stepped on the platform.
I guess I told you already.
And he's Acha, okay. Now check this one. Okay.
Get over.
Meanwhile,
what do you guys think is going to happen? I guess I told you already.
rotating in this direction. Okay. So his rotation, he's rotating the wheel in this direction. Okay. So that vector would be in this direction. Let this vector be omega. Okay. And why is he rotating the wheel? He's applying a torque in this direction. No? Okay. So that torque changes the direction of angular velocity. And now what is the angular velocity? The angular velocity is, means while he's rotating it become like this. Then Now, if you have seen the video, just look at this question. Okay. So in this question, a stationary platform P. Okay. That means this stationary platform. Okay. Which can rotate freely about a vertical axis. That means this platform can rotate about this axis. Okay. Supports a motor M and balancer weight N. So this is weight and this is the motor. Okay. The moment of inertia of the platform with the motor and the balance weight relative to the axis is equals to I. That means the moment of inertia of this entire motor plus this weight plus this motor, sorry, weight plus motor is nothing but N, sorry, I, about this axis of rotation. So this is the moment of inertia, I. Okay. Moment of inertia of the entire platform. Fair and fine. A light frame is fixed to the motor shaft with a uniform sphere rotating freely with angular velocity omega naught. That means this sphere, okay, is rotating with angular velocity omega naught. Okay, and the angular velocity direction will be nothing but this one, omega naught. Okay, about shaft VP. Okay, and the moment of inertia sphere, see, the moment of inertia of the sphere related to the rotation axis is equal to I naught. That means the moment of inertia of the sphere about this axis is nothing but I naught. Okay, I naught. Okay. I have to find out what the work performed by the motor in turning the shaft VP through 90-degree angle and through 180-degree angle. That means this motor is rotating like this. Okay, is applying a torque like this, and this spins the entire setup in that direction. Okay, clockwise. This is a 3D type of diagram. Understood? So from the video, you have learned that as soon as this motor rotates, the angular velocity of the sphere would be in this direction, omega naught, about z axis, isn't it? If this is x axis, if this is y axis, and if this is z axis, if the motor turns like this, the angular velocity, this omega vector, would be turning in that direction, no? Okay, and that would make this platform spin, isn't it? You have seen from the video. Okay, my question is, what would be the angular velocity omega of that spinning? Okay, so when the motor rotates the sphere, that changes the angular velocity of that changes the direction of angular velocity of the sphere in z-axis. What is the value of omega out here? Okay, my first question is, if the motor applies a torque like this, the torque vector is in this direction. If I consider the center, that means my origin is out here. Is there any torque about this y-axis? There is no torque about this y-axis, so I can easily write conservation of angular momentum along y-axis. Okay, so let me just draw the diagram. Okay, this is the sphere, this is angular velocity omega naught, and finally when the motor rotates, the angular velocity of omega naught is in this direction along negative z direction. And this was the platform. Initially the platform was moving with no angular velocity, and finally the platform will be moving with angular velocity omega. Okay, omega, this is nothing but omega naught, omega naught. Okay, one more thing, observe out here very properly. If the platform is moving with angular velocity omega, okay, look at the diagram. The platform is moving with angular velocity omega. That means this frame is fixed to the platform. So if the platform is moving with angular velocity omega, this frame would also rotate, no? So the sphere would have an angular velocity omega naught in this direction, but the sphere would also have angular velocity in this direction, isn't it? With same angular velocity omega. So now the sphere has two angular velocities, angular velocity along this direction and angular velocity along this direction. Okay, when it is rotated through 90 degree. So this was the initial case, and this was the final case. Okay. So I can apply conservation of angular momentum along y-axis. Conservation of angular momentum along y-axis. Okay. So see, if this is my y-axis, what was the initial angular momentum? Moment of inertia of the sphere. Okay, which is nothing but I naught, not I naught. This is nothing but I naught and I. So this moment of inertia is nothing but I naught. Moment of inertia of this sphere is I naught, and moment of inertia of the entire platform is I. So initial angular momentum about y-axis is nothing but I naught into omega naught. And one more thing, okay, see, whenever you hear vector, angular momentum is equals to I omega, torque is equals to how much? I into alpha, which is equivalent to linear momentum is equals to m into v, and force is equals to mass into acceleration. But in linear mechanics, this entire formula was something like this. Okay, so momentum is nothing but mass into velocity in x direction, I cap, plus mass into velocity in y direction, j cap, plus mass into velocity in z direction, k cap. Similarly, force vector was nothing but mass into acceleration in x direction, I cap, plus mass into acceleration in y direction, j cap, plus mass into acceleration in z direction, k cap. One thing you must notice out here is doesn't matter what the mass is. Mass in x component is same as mass in y component is same as mass in z component. Okay. See, similarly, mass in x component is same as mass in y component is same as mass in z component. But in rotational motion, whenever you try to do that, it creates a problem. See, if I try to write the same formula for rotational motion, okay, angular momentum is equals to I into component of angular velocity in x direction plus I into component of angular velocity in y direction plus I into component of angular velocity in z direction. Okay, and torque is equals to I alpha xi plus I alpha yj plus I alpha zk. Now, if you notice properly, suppose this is my axis, okay, x, y, and z. There is a particle out here that is rotating with angular velocity omega, something like that. Okay. Now, if I take moment of inertia about x-axis, moment of inertia about x-axis is nothing but m into r square. Okay. If I take moment of inertia about y-axis, moment of inertia about y-axis would be nothing but m into this square. Similarly, moment of inertia about z-axis is nothing but m into this distance from the z-axis square, isn't it? So moment of inertia through all the axes would be different. So while writing rotational terms, the formula expansion becomes moment of inertia. Okay, a total angular momentum is moment of inertia through x-axis into angular velocity in x component plus moment of inertia through y-axis into angular velocity in y component plus moment of inertia through z-axis into angular velocity in z component. Similarly, torque is equals to ixx into alpha x, iyy into alpha y, izz into alpha z. And this is the main formula that you must remember. Okay, this is naturally not taught in your 11-12 because while studying rotational motion, you only study one-dimensional rotational motion. Okay, that means your omega should be in one direction, and through that axis only you find out the moment of inertia and you apply all the torque and angular momentum. Okay, but the actual formula is nothing but this one. Fair and fine. Now see, since there is no component of torque acting in y direction or in y axis, there is no component of torque acting in y axis. Okay, why is the torque acting? Torque is acting along x axis. So I can simply apply conservation of angular momentum along y axis. And if I do that, what is the initial angular momentum? I naught into omega naught. So initial angular momentum was nothing but I naught into omega naught. Okay. Okay. What is the final angular momentum? Along y axis, I naught into omega plus I into omega. I naught omega plus I into omega. Okay. Obviously, this omega naught value is there, but this omega naught is along z axis. Okay. I'm not conserving momentum along z axis. I'm only conserving momentum along y axis. Now, if I solve this problem, omega is nothing but I naught omega naught divided by, wait a minute, I made an error out here. I naught omega naught minus, not minus, divided by, you can take omega common out here. I naught omega naught divided by I naught plus I is equals to omega. So this is the final angular velocity. Okay. Now the question is asking the work done by the motor. So work done by any force. I can simply apply work energy theorem. And what does work energy theorem says? Work energy theorem. Energy theorem. Change in kinetic energy is equals to work done by all the forces plus work done by all the torque. Okay. So final kinetic energy minus initial kinetic energy is equals to work done by motor. There is no other any forces doing any kind of work. Okay. Now what is final kinetic energy? Final kinetic energy is nothing but kinetic energy of the sphere plus kinetic energy of the platform. Okay, which is nothing but half I omega square plus half I naught into omega square plus I naught into this omega square. Okay, I naught omega naught square plus I naught omega square. I might have a question, sir. I understand this is I naught moment of inertia, but this is I naught and this is omega square. Fair and fine. But how do you know the moment of inertia through this axis is also I naught? This is a sphere, and for sphere, if I take the center as this one, okay, moment of inertia through y-axis would be same as moment of inertia through x-axis would be same as moment of inertia through z-axis. That means moment of inertia through any point that is passing through the center, okay, is same, which is nothing but 2 by 5 m square. Okay, so final kinetic energy, and kinetic energy is a scalar quantity, so I can easily add. So final kinetic energy of the sphere is nothing but half I into omega square plus half I naught into omega naught square plus half I naught into omega square. Understood? Initial kinetic energy. This is the final kinetic energy. minus initial kinetic energy. What is the value of initial kinetic energy? Initial kinetic energy, only this sphere was spinning, so half I naught into omega naught square. So half I naught into omega naught square. Okay, minus half I naught into omega naught square is equals to work done by motor. Okay, and if I see this, see out here, this half I naught omega naught square and this half I naught omega naught square would get cancelled. Okay, and so let me make this neat and clean. Okay, let me bring this close. So work done by motor is nothing but this value. Okay, half omega square. Let me take omega square common. Half omega square into I plus I naught. Okay, is equals to work done by motor. Now, what is the value of omega? The value of omega is nothing but we have found out little bit earlier. The value of omega is nothing but how much? I naught omega naught plus divided by I naught plus I. So this is nothing but, okay, or I naught omega naught divided by I naught plus I whole square divided by 2 into I naught plus I naught divided by 2. Now this is the value of work done. Okay, and if I just take some space here to solve it, so I'm bringing this out here, is equals to work done. Okay, let me cancel, or this would be nothing but I naught square omega naught square divided by I naught plus I whole square, okay, into I naught I plus I naught divided by 2. Okay, 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 this I plus I naught and this square will get cancelled. So if I bring this 2, okay, out here, I'll get my answer, or work done by motor is nothing but this one. Understood? So this is the first part of the question. Now the second part of the question. Second part of the question is the work performed if I turn it by 180 degree. Okay, so same type of diagram, but initial and final position would change. So I'm doing the question out here. Okay, out here. Okay, so same type of diagram. There is a sphere with moment of inertia I naught. Okay, I naught. It was initially rotating with angular velocity omega naught in this direction. Okay, and this was the platform. Platform was not rotating with anything. This was initial. And the motor rotated with by 180. That means final angular velocity would be in this direction. Okay, omega naught. And the motor is, sorry, the platform is out here. Platform is out here. And now the platform might spin with another angular velocity. I don't know which angular velocity. Let that be omega. Okay, this is final. Okay. For this problem also, I'll apply the same method. Same method means conservation of angular momentum along y-axis. So initial angular momentum is nothing but I naught into omega naught. Okay, final angular momentum. See, if this platform is moving with angular velocity omega, okay, this platform is moving with angular velocity omega. That means the frame out here is also rotating with angular velocity omega, no? And this omega naught is in opposite direction. So the net angular velocity of this sphere will be nothing but omega minus omega naught, isn't it? So final angular momentum is nothing but I naught into omega minus omega naught plus moment of inertia of the platform into omega. Okay, the platform is rotating with angular velocity omega. Understood? Now if I find it out, I naught omega naught is equals to I naught omega minus I naught omega naught plus I omega. Okay, what do I need to find out? I need to find out the value of omega. So it would become 2 I naught omega naught divided by I naught plus I naught plus I is equals to omega. Now if I want to find out the diagram, means work done. Work done is nothing but final kinetic energy minus initial kinetic energy, isn't it? Just wait a minute, okay? I explained something wrong out here. This frame out here was obviously rotating, okay? But this wheel, okay, is free to rotate. Free to rotate means the angular velocity of this frame, okay? The angular velocity of this frame is also moving with omega, no? If this platform is moving with omega, the angular velocity of this frame is not affecting the sphere. That means this is loosely connected. Okay, so this angular velocity won't be there. Understood? So this thing I have done it as wrong. Okay, okay. So if this angular velocity is not there, let me rectify my solution. So this is nothing but 2 I naught omega naught divided by I is nothing but the angular velocity omega. Okay. Now simply work done. Final kinetic energy minus initial kinetic energy. Final kinetic energy is nothing but half I into omega plus half I naught into omega naught. Kinetic energy is a scalar quantity, so it does not depend either omega naught is in upward direction or downward direction. Both will have plus half I omega naught square minus initial kinetic energy. Initial kinetic energy is nothing but half I naught omega naught square is equals to work done by motor. Okay. So if I cancel out this one and this one, okay, I'm just subtracting. Make the rest of them neat and clean. I'll get half I omega and half I. What is the value of omega? The value of omega is nothing but this one, half I omega squared. Okay, moment of inertia is nothing but square. Let me see if I've done. Yeah, motor half I omega square. Okay. Now what I did was I subtracted this and this term. Okay, and remaining term I made it neat and clean. Okay. Now work done by motor is nothing but half I into omega square. So 2 I naught omega naught by I whole square is equals to work done. Or work done is equals to half I into 4 I naught square omega naught square divided by I square. So I and square would get cancelled. 2 and this 4 would get cancelled to become 2. Okay. So my final work done is nothing but 2 I naught omega naught divided by, omega naught square divided by I is equals to work done. Fair and fine. Okay. Now let's look at the second part of the question. The second part of the question is asking, okay, the moment of external force which maintains the axis of arrangement in the vertical position after the motor has turned through 90 degrees. That means basically it is asking find out the torque exerted by the motor. Okay. This motor is rotating this entire thing in clockwise direction. No, this motor is rotating in this direction, so it is applying a torque in this direction. I have to find out the value of this torque. Okay. So if you understand carefully, what is the sole job of this torque? The sole job of this torque is to change the direction of this angular velocity. And previously, I have done gyroscopic acceleration for this gyroscopic torque, but the sole purpose of the torque was nothing but to change the direction of angular velocity. Remember? Okay. So that is nothing but gyroscopic torque. So gyroscopic SCOPIC. SCOPIC. Torque. The formula for gyroscopic torque is nothing but I into omega P into omega. So the formula for gyroscopic torque, sorry, just wait. Okay. The formula for gyroscopic torque is nothing but I into omega P cross omega. Okay. And the angle between omega P and omega is nothing but, see, omega P is in this direction. Okay. Angular velocity of precision. Because the torque is being applied in this direction. Okay. And omega naught is in upward direction. Okay. The angle between omega P and omega is 90. So sine 90. Okay. And wait a minute. Angular velocity of precision and angular velocity of rotation. Wait a minute. Precision velocity won't be along this direction. Precision velocity is the velocity that the wheel starts to rotate. Okay. This is nothing but angular velocity of precision. And when the rod moves in this direction with angular velocity omega, that is nothing but angular velocity of rotation. Okay. So angular velocity of precision is nothing but omega, which is nothing but is, or moment of inertia of the sphere, I naught into omega naught divided by I naught plus I. And omega is nothing but angular velocity of rotation, which is nothing but omega naught. So gyroscopic torque is nothing but I, moment of inertia of the sphere, okay, into I naught omega naught into I naught omega naught divided by I naught plus I into omega naught. So this I naught and I naught would become I naught square. So this is my torque out here. Understood? And this is the question to this answer. Okay. So let's move on to our next question. So this was our entire question. Understood? Okay. Now in this question, there is a rod out here. Okay. O dash. And assume this rod to be an axis. There is another rod out here, okay, of mass m and length n. This mass is m, this length is l. Okay, and this rod is rotating about angular velocity omega. Understood? Okay. Now the question is asking at what angular velocity of the rod the horizontal component of force acting on the lower end of the axis OA is equal to 0. That means what should be the omega such that out here horizontal component of force is equal to 0. Okay. So before we go into further details, let us study the free body diagram of the rod that is rotating. Okay. This is mass M and length L rotating. So out here it is supported by the hinge. Okay. And if the rod is rotating out here, it will experience a centrifugal force M omega square L by 2. Centrifugal force acts to the center of mass and downward force is mg. And since this rod is neither rotating downward nor rotating upward, okay, there will be a normal reaction force in vertical component which is equal to mg and normal reaction force in horizontal component which is equal to m omega square L by 2. And this normal reaction force is provided by this O dash axis. Okay, so I can simply write nx is equal to m omega square L by 2 and ny normal reaction force in y component is equal to mg. Okay, now if I see through this point, what is the torque through this point or what is the torque through this point? Okay, so torque through this point is nothing but mg into L by 2. And why did I find out the torque to this point? Because see, if out here the hinge was means a little bit weaker, the rod would try to fall down or rotate in this direction also, no? Suppose imagine a very heavy rod that is rotating with very less angular velocity in this direction. The rod would be like this, somewhat like this, isn't it? So the rod is trying to fall down and that torque is nothing but mg into L by 2. See, no other forces is causing torque. Ny into 0, nx into 0, and this the direction between r vector and this force is nothing but 0. So all these three forces will have 0 torque except this mg force. This much is understood. Okay. Now let us proceed to the free body diagram of the axis. Okay. So if I draw my axis out here, OO dash, FBD of axis, O dash. Okay. So out here, since this reaction force is in this direction, so nx will be in opposite direction. Okay, since ny is in upward direction, out here normal reaction force is in downward direction. Newton's third law, equal and opposite reaction force. And since this torque is clockwise, out here it will form an anti-clockwise torque. Okay, now I have to find out what is the normal reaction force out here. Okay, so see, someone needs to balance this ny, no? Otherwise this axis would keep on moving in downward direction. So suppose this was hinged or this was supported out here. Okay, I need to find out what is the reaction force applied on the by the hinge on this rod. It is nothing but ny only. Okay, let's say F2 in upward direction. Okay, and since this reaction is in rightward direction, let's say F1 is in left direction. So the question says out here, what should be the value of omega such that F1 is equal to 0? So let's balance it out. Okay, so torque about point A. I'm taking torque about this point. Okay, this is point A, point A, point A. Torque about point A. Torque about point A. Torque about point A is nothing but F1 into L by 2. Okay, plus F2 into 0. Understood this much? Plus, what is the value of torque or what is the value of this torque? This torque and this torque is Newton's third law, equal and opposite. So the value of this torque is nothing but mg L by 2. So torque about point is nothing but F1 into L by 2. Okay, minus how much? Minus how much? This torque is nothing but mg into L by 2. Mg into L by 2. And since this axis should not wobble, that means what? Net torque about this point is equal to 0, which is equal to 0. Now, if I just solve for omega, I'll get my answer. See, what is the value of F1? The value of F1 is nothing but ny. F1 is equal to ny is equal to mg. So F1 is equal to ny is equal to mg. So wait a minute. The value of F1 is not ny. Wait a minute, I made a mistake out here. The value of F1 is nothing but nx. So F1 is equal to nx. See out here, F1 is in horizontal direction, so this is be supported by this reaction force. Okay, which is equal to m omega square L by 2. Okay, so this is nothing but m omega square L by 2. So if I solve my equation, m omega square L by 2 minus mg L by 2 is equal to 0. Now if I bring this entire term to the right hand side, this will become plus, isn't it? Okay, and this 0 is getting omitted. So let's bring it closer. Let's bring it closer. Now if I cancel out the m from this side, I cancel out the L from this side, this side. I can also cancel out the 2 from this side and this side. I'll get nothing but omega square is equals to G. Acha, wait a minute. I forgot the thing. Wait a minute. Wait a minute. This is 4. So I have to multiply this L by 2 also, no? So L square by 4. L square by 4. Now if I cancel out M and M, L and L square, 2 and outside it would become 2. So omega square is equals to 2G by L, or omega is equals to under root of 2G by L. Understood? So this question was more or less simple enough on the simple category. So see this question. Okay. So in this question, there is this rod. Okay. And this rod is rotating about this axis. Okay. So this particle will rotate in this circle. Okay. This particle will rotate in this circle, and so on. This particle will rotate in this circle. This particle will rotate in this circle. Okay. So this is the phase of rotation. Okay. So this is my schematic of rotation. Now the question is asking, the first part of the question, the magnitude and direction of rod's angular momentum M relative to point C. That means with respect to this point C, what is the angular momentum of this rod? Okay, as well as its angular momentum relative to rotation axis. That means what is the rotation axis? This one is the rotation axis. What is the angular momentum relative to rotation axis? Okay, so let's solve the first part of the problem. So if this rod is rotating like that, the angular velocity vector would be in this direction, isn't it? This is the direction of angular velocity. Okay, now let's do one thing. Okay, let's just copy this image. Okay, and bring it out here. So I'll solve for this image. Okay, I'll solve for the value. Okay, so when the rod is rotating like that, my first angular velocity vector is in this direction, omega. Now the question is asking, what is the value of angular momentum about x, y, and z? Isn't it? Z is nothing but a vector that is going towards it. Okay, so what is the angular momentum about this x, y, and z axis? Understood the question? Okay. Now let me take this component, or let me take the value of this angular velocity omega. Okay, perpendicular to the rod, that means along this axis and along this axis. Okay, so the angular velocity of the rod along this axis would be nothing but omega cos theta. Okay, so along this axis is nothing but omega cos theta, and perpendicular to the axis is nothing but omega sin theta. Omega sin theta. Okay, let me also draw the axis. This is my perpendicular axis. Okay, and this is the axis that is along the rod. Now my second part of the question is, what is the moment of inertia of the rod, of this rod, along this axis? Okay, what is the moment of inertia of the rod along this axis? It is nothing but ml square by 2. Sorry, ml square by 12. So along this axis, it is nothing but ml square by 12. And along this axis, what is the moment of inertia along this axis? Along this axis is nothing but how much? 0. Why? Because every part of the rod is attached to the axis. Okay, I'm assuming 0 thickness. Okay, so if the thickness of the rod is 0, that means the distance of every particle of the rod from the axis is nothing but 0. Okay, very fine. So the entire angular momentum of the rod would be through this axis. And what is the angular momentum of the rod? Angular momentum of the rod about axis that is perpendicular is nothing but, let me draw it, is nothing but I into omega. I into omega. So what is moment of inertia? ml square by 12. And what is omega? Omega sin theta. Omega sin theta. This much we have got it. Okay, basically what I have done is I found out the angular momentum about this axis. Okay, and that is only angular momentum. Now see, the question is asking, find the value of angular momentum about this axis x, y, and z, about this coordinate. Okay, so this is the only value of non-zero angular momentum that I have. No, the value of angular momentum out here would be 0 because I out here is 0, isn't it? So angular momentum, okay, angular momentum is nothing but angular momentum along x, I cap, plus angular momentum along y, j cap, plus angular momentum along z, k cap, isn't it? That means what I'm basically doing is I'm taking this vector, okay, and componenting this vector along this direction, and z direction. Okay, so the component of this vector along this axis would be nothing but this angle cos something. So this is theta, this is 90 minus theta, and this is 90 minus theta, this is nothing but theta. So Lx is nothing but ml square by 12 into omega sin theta into cos theta, isn't it? Okay. Similarly, okay, one more thing. Lx has negative dimensions, negative thing. Why? Because see, if you take this vector, the component of the vector is along negative x-axis, no? So this negative is due to this negative x-axis. Understood? And the perpendicular component is nothing but ly, which is nothing but same ml square by 12 into omega sine theta. That means component of this vector along this axis, and this is nothing but 90 minus theta into cos 90 minus theta into cos 90 minus theta. And cos minus 90 minus theta, as you all know, is nothing but sine theta. So sine theta, and sine theta becomes sine square theta. Okay, so this entire thing becomes sine square theta. Understood this part of the question? So this is basically the first part of the question. Okay, so the first part of the question basically said find the angular momentum about this axis. So about this axis is nothing but this one, ml square by 12 into omega sine theta. Okay, and about this x, y, and z. About this x, y, and z is nothing but this value, which is nothing but basically component of this value along x direction, y direction, and z direction. Okay. Now the second part of the question: how much of the modulus of vector m relative to the point C increases during half a turn? That means this rod has rotated and gone like this half a turn. Okay. So let me draw the picture. Okay. So if I draw the picture out here, during half a turn, the rod would rotate like this, and similarly, I would have my angular velocity omega sine theta in this way. Okay. So after half a turn, if I say angular momentum along x, y, and z, okay. So apart from this value, okay, Lx, this sign would just change. Instead of going this in this direction, the x component of this value would be in the rightward direction. Okay, after half a turn. So I'll get my value something such as plus ml square by 12 into omega sine theta cos theta into I cap. And the j component, see, j component of this angular momentum, okay, of this vector would remain same as it is. So I'll write the j component same as it is, plus ml square by 12 into omega sine square theta. Understood? So this is my second part of the question, part B. Okay. Acha. Second part of the question asks change in angular momentum. Okay, change in angular momentum is nothing but final angular momentum minus initial angular momentum. So it's basically nothing but this value. This is final angular momentum minus this value. This is nothing but initial angular momentum. Okay. So this is final, this is initial. So if I subtract that, delta L. Okay. So see, follow properly. Okay. This minus of this. This is nothing but 2 times this one, isn't it? 2 times any other value. So m L square by 12 into omega sine theta cos theta minus of minus ml square by 12 omega sine theta cos theta into I cap, and see properly. This j cap, this minus this would become 0. So leave it as it is. Okay. So delta L is nothing but ml square by 6 into omega sine theta cos theta. Understood? Okay. Along I component. Okay. The third part of the question is asking find out the torque. Okay. So before finding out the torque, the thing that you must realize is this angular velocity. This vector is also rotating in this circle. Okay. That means after a certain while, angular velocity would be out here. Okay. Initially, the angular velocity was out here. After that, finally, the angular velocity out here. In the meantime, angular velocity would be in this direction, this direction, this direction, this direction. Okay. The angular velocity is also rotating with the rod. Okay. Okay. Now assume my initial direction of angular velocity. Okay, initial direction of angular velocity was in this direction. Okay, along theta. Okay, see the diagram. The initial value of angular velocity was in along this direction, isn't it? See, omega sine theta. Omega sine theta. So let me just draw that. Initial value of angular velocity was in this direction. Nothing but omega sine theta. Okay, and finally it was along this direction omega sine theta, isn't it? Okay, so let me draw the vector a little bit properly. Initial angular velocity sine theta omega sine theta. Now if you observe properly, this angular velocity vector is also rotating in this circle. Okay. Now let's say for time tt. Okay. Let's draw this angular velocity vector only for some time. Okay. So I have my angular velocity vector that is rotating with the rod. Initial angular velocity was along this direction. Okay. Omega sine theta. Final angular velocity was along this direction. Omega sine theta. Okay. So it started from here. It started from here, and the vector started rotating along this line. Okay. Fixed around this point. Okay. Let's say after time t, okay, and it is rotating with angular velocity omega. So the angular velocity of rotation is nothing but omega. That means this vector is rotating with angular velocity omega. Okay, along with the rod. Okay. Let's say after time t, the angular velocity vector reached out here. Okay. The magnitude is nothing but omega sine theta. How much is this much angle? This much angle is nothing but omega into t. Okay. And what is change in angular momentum for this time t? Change in angular momentum is nothing but final angular momentum minus initial angular momentum. And angular momentum is a vector quantity, or angular velocity is a vector quantity. Okay, let's not say change in angular momentum, let's say change in angular velocity. Okay, if I just multiply change in angular velocity with moment of inertia, I will get change in angular momentum. Okay, so let's say this was the final vector, this was the initial vector. What is this vector minus this vector? It is nothing but a vector, that is this one. Okay, so this vector. My question is, what is the value of this vector? What is the value of this vector? Okay, I need to understand the value of this vector. Okay, this vector is nothing but, see, if I just consider this portion, okay, as a circle, and this as the arc of circle, okay, this is angle omega t. So this vector is nothing but radius into angle. And what is radius? Omega sine theta. What is angle? Omega t. So this portion is nothing but omega sine theta into omega t. So change in angular velocity is nothing but omega sine theta into omega t. Okay, understood? It happened in time t. So change in angular velocity with respect to time, or change in angular momentum. Change in angular momentum is nothing but ml square by how much? 12. Okay, I'm writing this value. Moment of inertia ml square by 12 into omega sine. Acha, ml square by 12. I'm writing this value. Ml square by 12 into omega sine theta into omega t. Okay. See, in the previous case, it has been rotated by 180 degree. Okay. In this case, it has been rotated by some amount of degree. It hasn't reached this full distance out here. It has reached only this much distance. Okay, this much distance. Understood? So I'm calculating only for that much distance into omega t. So delta L by delta t, okay, is nothing but ml square by 12 into omega sine theta into omega t divided by t. It happened in time t, no? This t and this t would get cancelled. So delta L by delta t is nothing but ml square by 12 into omega square sine theta. Okay, understood? And if you observe properly, rate of change of angular momentum, or delta L by delta t, is nothing but torque, okay, on known as moment of force. So torque is nothing but this value. So this was our fundamental question that has answered this question. Okay, and this question carries a significance important in from JW perspective. Okay, so let's proceed to the next question.